going through him. The capacitor's got energy stored in it when he's got his plates all charged up and an electric field exists there. So these two guys are exactly out of phase with each other. And they too will exchange the energy back and forth, and when they do, it will look just like everything else in the simple harmonic motion world where you've got two energy stores that are equal and opposite, like this guy does. Okay, when you got a generator, you're going to get this oscillation because it depends on the angle of the stator to the rotor. And this thing that shows what phase it's in will actually go from minimum current to maximum current to minimum current to maximum negative current and back again by going around in a circle. And if you draw a little triangle here, this part here, the shadow, yeah, I guess you'd call it the shadow cast by the hypotenuse down on the horizontal axis, will grow and shrink and grow in the opposite direction as this thing goes around in its 360-degree cycle. And when it does that, it will do it in a sinusoidal way. So a sine wave represents a point on a circle and the projection it makes on the horizontal axis, or you can even say on the vertical axis for that matter, doesn't matter which. Both will be the same, they'll just be out of phase with each other. It'll be a cosine wave, it'll be a sine wave. That thing will actually tell you what the voltage will be at each point in the cycle. It'll actually be, the voltage that you'll get out of that generator will be the maximum voltage that's possible times the sine. They say the sine of omega t. Omega t is the rotational rate. It's the number of radians per second times the seconds. So that's what tells you how this thing came about. You got a maximum here. And by the way, a sine and a cosine can only be one at most. When this thing is down here and the hypotenuse, you know, anybody remember trig in high school? The sine happens to be the
opposite
the
over.
y over the r, meaning the side opposite over the hypotenuse. So basically, the most that you can have in the way of projection is whatever that hypotenuse is. So it'll always be 1 or less than 1. So it'll always go between +1 and -1, but multiplied by whatever that maximum voltage is. So that's how we represent oscillations. And that's how they got to be that way. They really are a thing that's spinning around at a constant speed, a point on a circle that's constantly rotating and producing that kind of output. And the kind of output they get you is an oscillation. Well, one of the things we talked about in our power supply was filters. Let's talk about them again. But let's apply them to the radio. Because that's really, you know, the reason we have capacitors and inductors is they have this magnificent feature where they respond to the frequency of the current going through them in perfectly opposite ways. So they can work together to fight each other in a sense, I guess you'd say. Like the example I gave a week ago. Let me just repeat that example because I'm going to use that many times. That thing is, I got to build me one of those. It's such a good teaching moment to talk about. AC power coming in, you go through an inductor, you go through resistance. In this case it's a light bulb, but it could just as easily be any other kind of resistance. Just because it produces light doesn't change the fact that it's still a resistor. And capacitor. And because it's alternating, as you go up in frequency, the capacitor conducts more current. The current will go up. As you go up in frequency, the inductor will, I should say this is the capacitor, and these are this is the amount of current. The capacitor will be able to conduct more current, and the inductor will be able plus, and at that point where if you vary one or the other, an example I had in my high school class, they put a slug in that coil to change the inductance to the point where whatever the inductive impedance here was, X sub L, which is 2 pi times the frequency times the inductance, or if you like, J omega L, and the capacitance, X sub C, which is 1 over 2 pi times the frequency times the capacitance, or 1 over J omega C. When those two equal each other, you got this condition called resonance, which is the point where they cancel each other out. This and this have no effect, and this thing will go full brightness. And that means you have the ability to discriminate by frequencies. If you had something like that on your radio, you could tune a particular radio station. Yeah. Now that's when they're in series. When they're in parallel, they actually do the opposite. They don't cancel each other out, they become maximum, because in this circuit, when you've got a low frequency, the current will go this way. It wants to go through the coil. When you get a higher frequency, it wants to go through the capacitor, because that becomes the lower impeding device. When you get the right frequency, it doesn't go through either one, it's blocked. You will get a voltage that spikes at that thing, at that point. In this case, you got a current that spikes at the resonant frequency. And if you got a voltage at that frequency of interest, and you amplify it, you made yourself a radio receiver. You've got a radio signal coming in, you select what frequency of radio signal you want by varying one of these two devices. I'll put an arrow through it to indicate that it's a variable device. And that's how you're going to tune a particular radio station. And what values you need come from this formulation here. It happens to be the point where 2 pi f sub L is equal to 1 over 2 pi fc, and if you solve for f, it's 1 over, and I did check independently, this is the formula. That's what you get if you derive it. The frequency at which you get resonance is when that condition exists, when the impedance of your inductor and your impedance of your capacitor are equal and opposite. If it's in series, you get maximum current. If it's in parallel, you get maximum voltage. That's the tuning part. That's the part that does the frequency selection. And you're going to do that many times in a radio because you're trying to not only select frequencies that go out in a transmitter, but go in a receiver. And you have stages of signal processing in each one of these guys. Let's go through that. Let's now finally get into the subject of radio transmitting and radio receiving. Next week I'm going to talk, by the way, about modulation, where you not only have a radio signal going through there, you put some intelligence in it so you can actually hear your voice, or put some data in there. You do something to vary the signal in a way that makes it possible to be heard. And you've heard of all these techniques because you've got a radio that has an AM band and an FM band. AM is modulation by amplitude changes, amplitude modulation. And the FM band is the frequency modulation band, where the frequency of the signal is varied in such a way that a human voice or music or sound or data or whatever gets put in it. So if I'm building a receiver, first thing I'm going to use is something to capture that radio signal. What part of a wave do you think is actually going to matter? Here's a radio wave, and it's got an electric field, and out of phase with it, it's got what's called a magnetic field, and they're 90 degrees to each other, and both perpendicular to the direction of propagation. They're moving from a point source to a destination. It's actually the H field, it's the magnetic field. Same reason we talked about before with Faraday's law. When a magnetic field goes through piece of wire, a current is created. So when the magnetic field goes through the antenna, current flows at the rate of that radio signal. And it so happens, as we know, when we spin the dial on a radio, there's not one, there's a million radio signals out there. They're all over the place. So we want the one that is of interest to us, and how do we discriminate against the ones we don't want? We have to look for a characteristic in that signal. That characteristic is frequency. You look on your dial on your radio, and what do you see? Frequencies. I want WGN, 720 on your dial. Well, that's really 720,000 cycles per second, 4 kilo, meaning 10 to the third hertz. Or you want WBBM, the 780, you want to listen to Rush Limbo, and he's 820, I guess. I don't know. Anybody here listen to him? No, let's not talk politics. But you pick the station you want by picking the frequency of the station that you want. And same thing in ham radio. I want to be on the 40 meter band, the 80 meter band, the 15 meter band, whatever. It's got a frequency start and end point. 40 meters starts at 7.0 megahertz, ends at 7.3. There are sub parts in it, like, I don't remember anymore, I think it's 7150. Below that's its theta, which means Morse code, radio teletype, all kinds of modes like that. Above that can be voice or data. And if you listen on 40 meters, you're going to find there's another unwelcome visitor there. There are broadcast services around the world that are in different regions than we are. The world's split into 3 regions. We are in region 2. And in region 1 and region 3, they happen to have shortwave broadcasting. So you're going to hear some of that ugly stuff late in the evening when the band starts to open up and the radio signals bounce off the ionosphere better. But there are other bands where you don't have that problem. Anyway, you want to pick a frequency. So how do you do that? You run that formula that says you're going to have to select a value for L, which is your inductance. It's measured in henries. And your value for C, which is measured in farads, which is a very large value, so you tend to find them in microfarads, 10 to the -6, or microfarads, picofarads, which is 10 to the -12. Very small amounts are needed. And you plug that into that equation, and you figure out, okay, I'll select the coil, now I have to figure out what capacitor. Well, I can't get a capacitor that big, let me pick a smaller inductor. Okay, now I can find a capacitor in the right range. Or you pick one that's in the range, and you figure out what inductor gives you that frequency and resonance. And in your receiver, you build a tuning circuit, like this. The current flows in here, flows out there, and it produces a voltage only at the frequency of interest. You have to pick these values to be what you want them to be. And if you can turn that dial and change that, the frequency of interest will shift to the different radio stations on the band. Now, coming in, the signal is pretty weak. It's usually on the order of microvolts, millionths of a volt. You're going to lose from, if you get a transmitting antenna here and a receiving antenna here, you lose about 30 dB. 30 dB is a factor of about 1,000 in power, just because you have an air link between your transmitter and receiver. But if you build a sensitive enough receiver, it doesn't matter. You'll get there. So what we do is we have some kind of an amplifier stage here called an RF amp. And its job is just to get that signal up to the point where we can operate. Now, let's go back again to this transistor I talked about earlier. I said you'll get about 0.7 of a volt drop between the current coming in and the current flowing through. Boy, I'm doing bad arrows today, aren't I? Which really means you need to get the incoming part, the signal that comes into this transistor is going to do your amplification to be higher than 7/10 of a volt. Usually a few volts would be nice. And it starts out as microvolts, so you got to multiply it by a few million, which means you need an amplifying circuit that does that. Just to give you some usable signal for processing, and they do that. But how can they do that? Because you just saw here that it takes 7/10 of a volt. How can you get a transistor to even turn on if you can't get enough voltage out of the air? The answer is they wire it differently. They actually produce this kind of a circuit. That's the input. That's the output. And actually what this does, it gives you what's called voltage amplification. So you don't get a lot of power out of it, but it becomes a way to get the tiny voltages up to bigger voltages. There's other ways to do it too. You can use what's called a metal oxide semiconductor that happens to have the input come to a gate. Then you don't have that threshold voltage. You need to turn it on. Very tiny voltages can actually have an effect here. So very minuscule voltage here can produce an amplification factor. And they do it multiple times. You put it in stages. One feeds another, feeds another, until you get the kind of voltage you need. That's the first step. The next step is you want to get, this is almost like doing the power supply. You got these multiple stages. You want to process the signal. The electronics engineers do signal processing. You want to go through a process where you want to strip the information out of the radio signal. So there's a thing called a demodulator. And you know what? I'm going to just leave it at that for now, because next week we're going to talk about modulation. It's almost 9 o'clock now. And we'll talk about the process for getting the information in.